picture of Grothendieck, Alexander Grothendieck. That's just to test whether you've looked at all the slides, of course. He died about a month ago. He was one of the greatest mathematicians of the 20th century. And he was working in very, very abstract mathematics. And his method was to generalize and generalize and generalize until things become trivial, well, for people like him. And so once he was lecturing and it was a prime number, he had a prime number p. Let p be a prime number. And one of the mathematicians in the audience raised his hand and he asked, can you give an example? P is a prime. Well, 57. 57 is not a prime, it's 3 times 9. Yeah. So 57 is now called Grothendieck's prime. Yeah. So he understood very, very abstract stuff which we cannot understand altogether, but he had difficulties with using a prime. 57. Okay. Oh dear, and now we want to calculate this cross ratio. Let's do it like this. Okay, now we know that it's negative. So that's dangerous, that's a test. Okay. This is really awful. Okay. So now we know that we can find homogeneous coordinates on the line such that one of the points has the coordinates 1, 0, the other 0, 1, the third 1, 1, and then the coordinate of the fourth is in fact a cross ratio. That was my definition. That's a nice definition, but is it practical to compute it? Okay. I think the way I would do it I would do it like this. So we go back to R3. We go back to the definition in R3. And I take V1 as a vector 4 minus 5, 0. Yeah? So it's the vector corresponding to this point. Yeah? And V2, I take this one. Yeah.
Maybe this is a stupid question, but this 4 minus 5 minus 0 thing is a ratio in itself, so it effectively defines not a point. Oh,
yeah,
a point is projective.
Yeah. Okay. This is a line. This is a point in projective place. Yeah. It's a line in R3, and I'm choosing a vector. Okay. Yeah. I could have chosen 6 and minus 8. It's a choice. Yeah, you're right. All right. Okay, and now I know this line in R3 is a plane through the origin. Yeah? So I'm thinking about this line as a plane through the origin. Okay. And these are 4 lines lying in this plane. Yeah? So I'm thinking about L is a plane in R3 through the origin in R3. Yep, by definition. And in this plane I have 4 lines. A, B, C, D. And on the lines A and C I've chosen a certain vector. On the line A I've chosen a vector V1, and on line C I've chosen a vector V2. This is what I did. Yeah? Okay. And now I have to express these 2 lines in terms of this basis. Yeah? Now the awful. Now we have to use fractions, which I'm really scared of. So let's define V3 as this vector. So I've chosen the vector V3 on B, V3. And now I have to express V3 as a linear combination of these two. Oh dear. Well, this is just linear algebra. Or maybe it's not so bad. No. So, it looks bad because we seem to have 3 equations in 2 unknowns. So you would expect, why do they have a solution? Why do they have a solution?
A lot of zeros.
Yeah, because the 3 points are not arbitrary, they are on a line. Okay. So if we haven't made a mistake up there, it should be okay. So we have this equation 3 equals 4 lambda. Oh, that's easy. And we have 0 equals minus 5 lambda plus 3 mu. And we have minus 5 equals minus 4 mu. So, what do we find? Lambda equals something. And mu equals something. So I've used the first and the third. And if we're really brave, we check whether the second is true. We should? Okay. Right. Yeah, that's correct. Right.
That's easy.
Okay. So that's one part. And I continue.
Last question.
Now we have, of course, we have to choose a vector v4 here and express that vector in terms of v1 and v2. Yeah? So we have now expressed v3 in terms of so I'll write the answer here. Oh, sorry. v1 plus. Yeah, this is correct? Yeah. Okay. Okay. When we've done that, I can erase this into the next computation here. You don't need the computation, you only need the result. Okay, the next computation, let's take V4 of D, 1, 1 minus 3. So, there we go. V4, it's a new lambda and a new mu. Okay? So what do we have? 1, 1 minus 3 equals lambda times 4 minus 5, 0 plus mu times 0, 3 minus 4. So 1 equals 4 lambda, 1 equals minus 5 lambda plus 3 mu, minus 3 equals minus 4 mu. So lambda equals 1 over 4, and mu equals 3 divided by 4. And then this should be true. And it is. Yeah. So I know, I only need the result. So, okay. Okay, now I can erase it.
You could call coefficients.
Boring computation.
Okay, so now we use homogeneous coordinates on this line L. Line L we're looking at. Yeah, what line L? Defined by V1, V2. V1, V2 is the basis of L viewed as a plane in R3. Well, that's easy. This is, of course, this has coordinates 1 and 0. 1 times v1 plus 0 times v2. So v1 is 1, oh sorry, v1, I mean the line represented by v1, so A, capital A. Capital B, no, this was C, wasn't it?
C, yes.
Yeah. C, 0, 1. Then B corresponds to V3, and that is 3/4, 1/4, 5/4. Yeah? Okay? But of course here we can just use ratio 3 to 5.
Yes.
It's the same point.
I missed the first part, but you just stated A equals 0, 1, 0, and C equals 0, and you just
Yeah.
shoot that.
Okay, so that now we go back to the definition of homogeneous coordinates. It comes from linear algebra. V1, V2 are a linear algebra basis of this plane. There are 3. I can express this vector, this vector, this vector, this vector in this basis. This has coordinates 1, 0, 0, 1. And here we have computed the coordinates.
The relationships.
Yeah. Okay. And when I go from the Euclidean plane here to the projective line, I use columns instead of commas. I am only interested in the ratio. For example, of course, if I multiply both numbers here by 4, I get a vector which is 4 times this vector. It's a different vector in this plane, but it's the same line. And we are talking about projective points which are lines. So now we are talking projectively. Yeah. Okay. So that's D. It's 3 to 5. And then D, 1 to 3. Yeah? And now we can compute this cross ratio, and let's hope it's negative. How did we define it? C minus A, D minus B, C minus B, D minus A. Okay? And now we get a difference maybe with Stillwell's approach. Stillwell uses inhomogeneous coordinates, so he would write 3/5 ratio to 1, 1/3 ratio to 1, and this would be infinity to 1, and this would be 0 to 1. Yeah? Okay. I use homogeneous coordinates in order to avoid working with infinity. We can do both and see whether we get the same result. Okay? And then you have to interpret this as a 2×2 determinant all the time. Yeah? So this here is the 2×2 determinant of, well, it doesn't matter how you do it as long as you are consistent. Let's take C in the first column and A in the second column. But it doesn't matter as long as you're consistent. Yeah? C in the first column, 0, 1. A in the second column, 1, 0. Yeah? And then the determinants, D and B. So 1, 3, 3, 5. CB, C, B, D, A. C, A, D, B, C, B, D, A. I think it's correct. Okay. And now now we have to compute these determinants, and I'm going to compute the determinant and then erase it and replace it by the number. This determinant is 0 minus 1, so this is minus 1.